In late March of 2026, a small group of researchers briefed United States government officials on something they'd found using artificial intelligence, and one of the scientists involved described his own reaction afterward in blunt terms. This is the first paper I've personally ever written where I genuinely thought this has implications for society. A cybersecurity researcher at one of the companies responsible for securing a significant fraction of the entire internet called the underlying result a real shock. And within days, that same company had publicly moved up its own deadline for protecting itself against this exact threat by 6 years. This is the real story of how artificial intelligence helped researchers working alongside Google discover a way to build quantum computers using 100 times fewer atoms than anyone thought was possible. Why that specific reduction matters enormously for how soon a quantum computer capable of breaking internet encryption could actually arrive. And why even the researchers who made the discovery are being genuinely careful about exactly how they're choosing to talk about it. If you want real technology stories explained accurately instead of hype, subscribe now, because this specific story is still actively unfolding, and it affects considerably more than the tech industry alone. Let's start with the actual threat driving this entire story, because understanding why anyone would care about quantum computers and encryption in the first place requires understanding what's actually at stake. Nearly everything digital that relies on staying private, WhatsApp messages, banking transactions, medical records, classified government documents, is protected using encryption, mathematical systems specifically designed so that unscrambling that protected information without the correct key would take even the most powerful classical supercomputer considerably longer than the current age of the universe to accomplish through brute force alone. That enormous time scale is precisely what makes modern encryption trustworthy. A quantum computer, however, built using fundamentally different principles of physics, could theoretically perform that same unscrambling process in a matter of days rather than billions of years, once it reaches sufficient scale and capability. Today's actual quantum computers remain far too small and far too limited to pose that kind of threat right now. But a survey conducted in 2025 by the Global Risk Institute found a 39% chance that this specific situation changes within the next decade. As quantum computers continue growing more powerful and the algorithms running on them become steadily more efficient, meaning smaller and smaller quantum computers become capable of breaking encryption that currently requires a machine far larger than anything that exists today. If a story built on real, verified reporting from Time magazine and named researchers directly involved is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. It's worth understanding a specific concept that makes this entire threat considerably more urgent than it might initially sound, something security researchers refer to as harvest now, decrypt later. Even though today's quantum computers remain far too limited to actually break modern encryption, that doesn't mean encrypted data intercepted today is automatically safe from a quantum computer that gets built years from now. Malicious actors, including hostile intelligence agencies, are already believed to be systematically collecting and storing enormous quantities of currently unbreakable encrypted internet traffic, with the specific intention of decrypting it retroactively once sufficiently powerful quantum computers eventually become available. That means the actual security risk isn't simply about protecting communications that will happen after a dangerous quantum computer gets built. It's about protecting communications happening right now, today, that could still be exposed years down the line if the transition to quantum-resistant encryption doesn't happen quickly enough. That's precisely why a research result suggesting a dangerous quantum computer might arrive considerably sooner than previously expected carries such immediate urgency, even though the actual quantum computer capable of exploiting it doesn't exist yet, because sensitive information transmitted today could still end up compromised the moment it eventually does. Because of that growing risk, the U.S. National Institute of Standards and Technology, generally known as NIST, has set a formal 2035 deadline for organizations to transition toward new, quantum-resistant encryption methods designed to remain secure even against a sufficiently powerful quantum computer. That deadline was meant to give the world roughly a decade of advance warning, built around researchers' best existing estimates of how long it would realistically take quantum computing technology to reach a genuinely dangerous scale. The research at the center of this video suggests that timeline may need to move up considerably, and artificial intelligence is the specific reason why. If you found this background on the actual stakes involved as useful as I did while researching this, drop a comment and let me know. It genuinely helps me figure out what to cover next. It's worth understanding what quantum-resistant encryption actually means in practice, because it isn't simply a stronger version of the encryption already protecting the internet today. Modern encryption standards, the kind protecting your bank account or your private messages right now, generally rely on mathematical problems that are extremely difficult for classical computers to solve. but that a sufficiently powerful quantum computer could theoretically solve using fundamentally different quantum algorithms specifically designed to exploit weaknesses in that underlying math. Quantum-resistant encryption, sometimes called post-quantum cryptography, instead relies on entirely different categories of mathematical problems, ones that remain difficult even for a quantum computer to solve efficiently, based on current theoretical understanding. Transitioning the entire Internet's infrastructure from one encryption standard to an entirely different one isn't a simple software update either. It requires coordinated changes across an enormous interconnected web of hardware, software, and infrastructure providers worldwide, which is precisely why organizations like NIST set such a long runway for the transition in the first place, and why suddenly needing to compress that runway by 6 years, as both Google and Cloudflare have now done, represents a genuinely significant, resource-intensive undertaking rather than a minor scheduling adjustment. Here's where the story gets genuinely interesting. Because the breakthrough itself didn't come from simply building a bigger, more powerful quantum computer. It came from a research team at a quantum computing startup called Oratomic, working alongside collaborators, including physicist John Preskill, a widely respected pioneer in the quantum computing field based at Caltech. Discovering a fundamentally more efficient way to actually build the atomic quantum computers, researchers have been pursuing for years. To understand why their specific discovery matters, you need to understand a basic engineering problem that's been slowing down this entire category of quantum computer. Qubits, the basic unit of information in any quantum computer, are notoriously fragile, easily disrupted by tiny environmental disturbances, including background radiation from cosmic rays originating from the sun. The standard solution to that fragility has been redundancy, spreading a single unit of quantum information across many individual physical atoms simultaneously, so the overall system keeps working correctly, even if some of those atoms experience an error. In atomic quantum computers specifically, that redundancy requirement has typically meant needing somewhere between 100 and 1,000 individual atoms just to reliably encode a single, stable qubit. The algorithm Oratomic's team discovered requires just 3 atoms to encode that same single qubit, an improvement that reduces the total number of physical atoms needed to build a working atomic quantum computer by roughly 100 times. Dolev Blivstein, one of the paper's authors and an Oratomic co-founder, described the significance directly to Time magazine, stating plainly that people who genuinely understand what this means will immediately recognize its implications, and that in his own assessment, the world is not currently prepared for what this specific advance actually represents. If you found this specific technical breakthrough as significant as I did, drop a comment and let me know. It genuinely helps me figure out what to cover next. Here's the part of the story that makes this genuinely different from a typical incremental research announcement, because artificial intelligence wasn't simply a helpful tool used somewhere in the background of this research. According to Robert Huang, one of the paper's authors who previously worked directly at Google Quantum AI before leaving in 2026 to help co-found Oratomic, the team's initial version of their key algorithms actually performed roughly 1,000 times worse than what they eventually achieved. Bad enough, in Huang's own words, that the entire approach simply wouldn't have worked at all in that original form. Rather than abandoning the idea, Huang decided to try using a tool called OpenEvolve, an open source system that harnesses large language models, including Google's own Gemini and Anthropic's Claude, to iteratively optimize algorithms through a process modeled loosely on natural selection, testing and refining thousands of different variations in search of genuine improvements. Huang was candid about his own low expectations going in, stating plainly that he didn't actually expect the AI system to find anything useful at all. He was wrong. The AI combined existing scientific results in ways Huang and his colleagues described as genuinely novel, demonstrating a real, working understanding of niche, highly specialized quantum computing subdisciplines as it worked through thousands of different potential approaches. Without that AI-driven optimization process, Huang suggested the team likely would have tried a handful of manual approaches, watched them fail to produce meaningful improvement, and reasonably concluded the entire underlying idea simply wasn't viable at all. John Preskill, reflecting on the same result, offered a carefully balanced assessment, expressing genuine surprise at how dramatically the required qubit count had been reduced, while specifically emphasizing that human researchers remained the primary drivers of the actual research, asking the right underlying questions and then carefully guiding the AI's proposals toward genuinely useful, scientifically sound answers, rather than simply accepting whatever the AI produced without proper scrutiny. It's worth understanding a bit about the specific type of quantum computer this entire breakthrough actually applies to, because not every quantum computing approach benefits equally from this discovery. Quantum computers can be built using several fundamentally different underlying technologies, including superconducting circuits, the approach Google has primarily used since 2014 for chips like Sycamore and Willow, and neutral atom systems, which use individual, carefully trapped and controlled atoms suspended using precisely tuned lasers as the actual physical qubits. Oratomic's breakthrough specifically applies to this neutral atom approach, dramatically improving its underlying efficiency without directly affecting the resource requirements of superconducting quantum computers built using Google's more established technology. Umesh Varazani, a quantum computing researcher at UC Berkeley, described the broader challenge of choosing between these competing approaches as the field's genuine million-dollar question, since nobody yet knows with certainty which specific underlying technology will ultimately prove easiest to scale up to the kind of size needed for genuinely dangerous encryption-breaking capability. Google itself has hedged across both approaches, maintaining its long-standing superconducting research program while also investing directly in Quera, a company specializing in neutral atom quantum computers, back in 2024, and then launching its own dedicated internal neutral atom initiative just one day before its accelerated security timeline was announced this past March. It's worth being genuinely careful and precise about exactly how settled this specific result actually is, because responsible reporting requires holding real uncertainty alongside real significance. As of this reporting, the Oratomic paper has not yet completed formal peer review, and independent experts have raised legitimate, specific concerns about some of the underlying assumptions involved. Jeff Thompson, an associate professor at Princeton and the CEO of a separate atomic quantum computing startup called Logical, noted directly that many of the paper's core assumptions remain genuinely untested, and pointed out that it becomes considerably easier to dramatically shrink the theoretical size requirements for a quantum computer if you simply assume access to better performing qubits than currently actually exist in working laboratory hardware. That's a meaningful, substantive caveat, not a dismissal of the underlying research, but a genuine reminder that a result this significant and this recently announced deserves continued scrutiny before the broader scientific community treats its most dramatic implications as fully settled. Even accounting for that appropriate caution, the reaction from people directly responsible for securing major portions of the internet was immediate and genuinely serious. Bas Westerban, a cybersecurity researcher at Cloudflare, a company responsible for securing a substantial fraction of global internet traffic, described the research bluntly to Time as a real shock, adding that his own team would need to significantly speed up their preparation efforts in direct response. Within days of the research becoming public, Cloudflare formally announced it was accelerating its own internal deadline for transitioning to quantum-resistant encryption to 2029, a full 6 years ahead of NIST's original 2035 target. Westerban was direct about the actual stakes involved if that transition doesn't happen quickly enough, warning that a sufficiently capable quantum computer arriving before the broader shift to quantum-resistant encryption is complete could lead to genuine data breaches, extortion attempts, and businesses being forced offline entirely, describing the underlying risk as one where almost every system in the world becomes vulnerable simultaneously to an attacker equipped with a working quantum computer. Cloudflare wasn't reacting in isolation either. Just one day before the Oratomic paper was published, on March 25, 2026, Google itself announced its own accelerated timeline for securing its internal systems against quantum computing threats, also targeting 2029 rather than waiting for NIST's original 2035 deadline. That timing is worth sitting with directly because it means one of the largest technology companies in the world moved up its own internal security deadline by 6 years in the same general window that a closely related piece of quantum computing research was about to become public. A sequence of events that strongly suggests Google's own internal assessment of this emerging risk closely tracked the broader concern driving Cloudflare's and other researchers' reactions. It's also worth understanding how this specific research connects directly back to Google's own broader quantum computing strategy, because the Oratomic team's breakthrough didn't emerge in complete isolation from Google's own work. Robert Huang had previously worked directly within Google's quantum AI division before departing to help found Oratomic, and according to Time's reporting, he had informally mentioned to a former colleague still at Google that he'd been using AI and seeing what he described as lots of crazy results months before the formal papers were ever published. Shortly afterward, Google posted a job listing specifically seeking a quantum researcher to help develop AI-based discovery pipelines. And on March 24th, just one day before Google's own accelerated security announcement, the company separately announced an entirely new internal initiative focused specifically on atomic quantum computing. A Google spokesperson later confirmed to Time that the company had been assessing atomic quantum computing approaches for multiple years already, and had been publishing its own research on using AI for quantum error correction for years as well, characterizing newer entrants like Oratomic as now pursuing similar underlying ideas rather than working from a completely novel starting point. There's a broader, genuinely significant point buried in this entire story worth sitting with, one that extends well beyond quantum computing or encryption specifically. AI leaders have spent years promising that artificial intelligence would eventually accelerate scientific discovery in a general sense. This specific case represents one of the more concrete, well-documented examples of that promise actually playing out in a genuinely high-stakes research area, an AI system finding a real, scientifically meaningful improvement that a team of expert human researchers had already tried and failed to find on their own in a field with immediate, direct implications for global cybersecurity. That's precisely why Dolev Blivstein described this specific paper as unlike anything he'd worked on before. A moment where a piece of technical research suddenly carried implications extending well beyond the immediate research community into the security of essentially every digital system currently in use around the world. It's worth being clear, too, about how the researchers themselves have approached the responsibility of publishing a result with these kinds of implications. According to Blivstein, the Oratomic team briefed relevant U.S. government officials before ever publishing their findings publicly, and made deliberate decisions about exactly which parts of their underlying methodology were responsible to include in the initial published paper, with plans to publish additional detail about their specific use of AI in a separate follow-up study. That kind of careful, staged disclosure reflects a genuine effort to balance the scientific value of transparency against the real security risks of publishing a complete, detailed roadmap that could potentially help build a dangerous quantum computer, faster than defenders can prepare for it, though the authors themselves have been explicit that many open challenges remain before anything resembling a genuinely dangerous, encryption-breaking quantum computer could actually be built using this approach. So, what does all of this actually add up to? Researchers working alongside Google discovered, with meaningful help from an AI system originally designed to optimize scientific algorithms, a way to build atomic quantum computers using roughly 100 times fewer atoms than previously believed necessary. A genuine, if not yet fully peer-reviewed, breakthrough that multiple independent cybersecurity experts have described as a serious enough development to justify moving up their own security timelines by years, not months. Google itself accelerated its internal quantum security deadline to 2029, matching Cloudflare's own similarly accelerated response, both arriving well ahead of the previously established 2035 industry deadline. There's also a broader, genuinely significant point buried in this entire story worth sitting with, one that extends well beyond quantum computing or encryption specifically. AI leaders have spent years promising that artificial intelligence would eventually accelerate scientific discovery in a general sense. This specific case represents one of the more concrete, well-documented examples of that promise, actually playing out in a genuinely high-stakes research area. An AI system finding a real, scientifically meaningful improvement that a team of expert human researchers had already tried and failed to find on their own in a field with immediate, direct implications for global cybersecurity. Whether this specific pattern, human researchers hitting a genuine wall, then turning to AI-driven optimization tools and finding a breakthrough considerably faster than traditional research alone would have delivered, becomes a repeatable model across other fields of science remains an open question. But this particular case gives that broader promise a genuinely concrete, well-documented example to point to, rather than simply another speculative claim about AI's future potential. There's a genuinely important distinction worth holding on to as this story continues to develop, one that separates legitimate concern from unnecessary panic. Nobody involved in this research, not Blivstein, not Huang, not Preskill, has claimed that a dangerous, encryption-breaking quantum computer already exists or is imminent within months. What they've established is that a specific, previously assumed hardware limitation turned out to be considerably softer than expected, and that artificial intelligence played a real documented role in finding that out faster than human researchers, working alone, likely would have managed on their own. That's precisely why the responsible reaction from companies like Google and Cloudflare wasn't panic, but acceleration, moving up already planned security transitions by several years, rather than treating the threat as suddenly, immediately upon us. Understanding that distinction, real acceleration of a known, well-understood risk rather than a sudden, unprecedented emergency, is exactly what separates an accurate account of the story from an exaggerated one. It's also worth remembering that the researchers themselves, the people with the deepest, most direct understanding of exactly what this breakthrough does and doesn't yet enable, are the ones being most careful about how they characterize it, briefing government officials, staging their disclosures deliberately, and explicitly acknowledging that many open challenges remain before anything resembling a genuinely dangerous quantum computer actually gets built using this specific approach. If stories like this, grounded entirely in real, verified reporting instead of exaggerated headlines, are what you come here for, subscribe to this channel and turn on notifications, because this specific story is still actively developing. And there's a very real chance the next update changes how soon this particular threat actually arrives. Thanks for watching, and I'll see you in the next one.